A2 Maths, differentiating sine and cos. Okay, so what you've got in front of you is this graph of the function sine x. What we're going to do is we're going to look at working out the gradient at a couple of the key points, 0, 1, 2, and so on. Notice that your graph is in radians. It has to be in radians for us to even investigate any sort of calculus with the trigonometric functions. So we're going to go through, we're going to look at just working out the gradient function at some of these key points. Now the way you work out the gradient at some of the key points is by forming a gradient triangle. So if we look at the result for 0, or 1 in this case, first of all. So if we look at the gradient at 1, we can draw ourselves a tangent line and then roughly calculate what the gradient is of that line. So looking at this, you can see we go roughly up 0.6 and roughly along about 1.1. So the gradient at 1 can be calculated to be about 0.54. So using that idea, you could go through and you could work out the gradient at these values here, all the way across. Okay, right. So we're just going to have a look at some of those. So yes, roughly at 0, it's going up about the y-x line, so it's going up to a gradient of 1. When you get to number 2, it's coming down now, so it's got a gradient of minus 0.42. At number 3, it's getting quite steep going downwards, which is roughly about minus 0.99. Number 4, it's shallowing off again, so it's about minus 0.65 because it's still going down. And when you get to 5, it's gone past the minimum point, so now it's going back up again, but quite a shallow gradient, about 0.28. And then finally at number 6, just over here underneath the equation, about 0.96. So now we've got these values, these rough sort of values that we figured out. What we can do is we can actually plot those onto our graph. And if we plot these onto our graph, we're going to investigate what that equation looks like then. So this is our gradient function we're going to plot down now. So on our sketch, if we plot down some of these values, so at 0, we can see the value is going to be 1. At 1, it's roughly about 0.54, so that's roughly about there. At number 2, sorry, it's minus 0.42, so that's roughly about there, and so on. There you go, 0.99, 0.65, 0.28, about there, and 0.96, which is up there. And we can see we've got the graph that's sort of coming down like this, turning, going back up there to that. And if you haven't spotted, you can see that the graph you've drawn, which is the gradient function, is actually the equation of y equals cos x. So the gradient function of y equals sine x is the gradient dy over dx equals cos x. That's a bit of a guess with those few values, but you can clearly see those values fitted perfectly on that gradient line. That rule is true. Okay, so we're going to do the same sort of idea with cos. So sine definitely differentiated to cos x. What about the differentiation of cos x? So if we plot those values, we can see I've done that for you. So I've calculated the values already. And just have a go at plotting those. So at 0, it's minus 0. is 0. At number 1 is minus 0.84, so that's about down here. And so on. 2 is about minus 0.91, 0.14, 0.76, 0.96, and then 0.28. And so we can see we've got a graph that's going to come down like this, around up there, and then back down again. And you can see it's going to form another trig graph, very similar to sine x, except it's upside down. Sine x usually goes up like this. So if we look at it, the graph is going to be minus sine x. So when we differentiate y equals cos x, it fits really nicely with minus sine x. Okay, what about the gradient function of 2 sine x? What difference would it make having a 2 in front? Well, very similar to when you've differentiated functions to do with x or x squared or x cubed. If you're thinking about something like 2x cubed, you notice that 2 stays at the front. It doesn't affect the gradient part. So you differentiate in sine x, which we know goes to cos x, and the 2 remains there, doesn't affect it. What about if you've got a gradient of sine 2x? Now it's slightly different because the 2 is within the function of sine. If it's outside, it just stays there. But if it's inside, it does change it slightly. So this is a graph of y equals sine 2x. Now what's important to notice is the gradient straight away gets quite steep. So it's steeper when it first starts. Before, it was just y equals sine x. It started off at 1, whereas the sine 2x is a lot steeper. So that means that the gradient function is 2 lots of cos. But it's also important to notice that the period will remain the same. When it gets round to here, it's gone up, it's gone back down again, the gradient line, and it's gone back down here. It's going to finish back there and repeat. So the period of it is exactly the same. So what does that mean? Well, if that's 2x there, it will remain as 2x in its final answer. So the gradient function is 2 lots of cos 2x when you started off with y equals sine x. Okay. These gradient functions you've got to learn. So if you've got a sine bx, if you're dealing with a sine function, that's going to go to ab cos bx. If you've got your initial function as a cos bx, it goes to something very similar. The a stays at the front, the b comes to the front, but it goes to minus a sine bx. And it's worth remembering, if you think about the sine function, it starts off by going upwards, starts at 0 and goes upwards, it goes positive. That's why sine goes to positive cos. Where the cos function starts at 1 and goes downwards, it goes negative straight away. That's why that goes to a negative gradient. But you've got to learn which way round they go. Okay, just make sure you've got those in your notebook before you move on. We're going to look at proving those later with first principles. Okay, so same idea, but this time we're going to investigate a exponential curve. So if I look at 2x, I've done the work again. I've gone through, calculated each of the gradient triangles, and I'm going to plot these just to plot the gradient graph. So when we get to minus 3, which is about here, it's quite a small value, about 0.09. Minus 2 is about 0.17. Minus 1, about 0.35. 0 is 0.69, which is quite important. It's not 1. 1 gets you 1.39, and so on, 2.77 and 5.5. So when I plot that, I've noticed that the gradient graph of y equals 2x is also another exponential function. So an exponential function to start with, like y equals 2x, its gradient function is another exponential function. What we're going to look at is how to actually show what the equation is of that. So what we're going to do, we're just going to look at the graph of y equals a to the power x. If you've got a graph plotter yourself, great, but if you don't worry, we can just go with this part of the explanation. So we notice that when we look at different values of y equals a to the x, sometimes the exponential function goes above it. So we might have a situation where if this was our exponential function, like that, sometimes the gradient function goes above it, and sometimes the gradient function goes below it. It depends on the value of a. Now what we noticed is to actually let it land exactly on top of itself so that the gradient function equals the original function is at a very special value, and that value is e, the exponential value. So that's what we were just showing, or we had investigated using a graph plotter. So we know that for the value e, that when you differentiate it, you also get exactly the same exponential function. So if I've got y equals e to the x, its gradient function is exactly the same, e to the x. For all other exponential functions, they change slightly and we'll look at the general form for y equals a to the x in a minute. So you need to learn that for some function like a e to the bx, then your gradient function will be, same as before, the b can come to the front, so a b e to the bx. That's the general rule for differentiating exponential functions. We'll look at doing that when you hear something called the chain. So what we're going to look at is we're going to look at the gradient function for any exponential function. So any exponential function can be written in this form. F of x equals some number, which is a constant, to the power kx, where k is also some constant number. So it could be something like 2 to the power 3x. So a and k are just constant values. Now the first thing we're going to do to show how to differentiate this is just to rewrite a to the kx using the exponential function. And the reason why we can use the exponential function is because we can know how to differentiate the exponential function. We don't know how to differentiate this a part as a base there. So the way I'm just going to convert it is by using not just the exponential function, but also its inverse. So I'm going to do this. So the exponential function and its inverse, which is a natural logarithm, basically cancel each other out. They're using e to the power ln, and because the exponential function and the natural logarithm are the inverse function of each other, those two will cancel each other out, leaving you just a to the power kx. That's why these two are exactly the same. It's exactly the same idea as timesing by 2 and then dividing by 2. Because timesing by 2 and dividing by 2 are the inverse of each other, they cancel each other out. Okay, so it's a little bit of a leap, but that part will make sense in a minute. Right, so what we can do now is you can use our law of logarithms. And the law of logarithms says if you have ln a to a power, we can bring that power to the front. So we end up with e to the power kx ln a. So kx is just a number that we can bring to the front. Now what we can do is you can rearrange this. We can rearrange it because k ln a is a constant. We can just pull that constant to the front, noting that k ln a is just some number, just some constant value. So those two values there, k and a, as we said earlier on, could be something like 2 to the power 3x. So the 2 and the 3 are just constant numbers. And because it's just a constant, what I can do now is I can differentiate it. Because the previous rule said e to the ax goes to a e to the ax. So that's what I'm going to use. Okay, so k ln a is a constant. I'm going to use this rule here. Just use the b value to show the difference. But if I differentiate e to the bx, it goes to b e to the bx. Now in this case, my b value is k ln a. So the k ln a can come to the front, e to the k ln a x just there. What does that mean? It means that now I can rearrange this back to like it was at the start. So the e or the k can go to the top with the x. So I'm going this step in reverse from there to there. And why do I do that? Because now I can look at getting rid of that e ln. So I end up with this as my final answer. What's the differentiation of a kx? It is k ln a to the power kx. Okay, you've got to learn that formula. You do not get given it. Okay, so you do need to learn how to differentiate any exponential function. You should also learn how to formulate that, like we just saw, but most likely in the exam that you just have to remember and be able to apply that rule from there to there. Right, so what we're going to do is just going to have a go at practicing some gradient functions. So get ready to pause and then move on when you're ready. So the first one I'd like to look at is e to the 3x. So pause. Okay, so you should have got 3e to the 3x because the 3 just comes to the front. Okay, try this one. 7e to the 6x. So again, pause. Okay, so you should have got 42e to the 6x because the 6 can come to the front, multiply by the 7, 6 times 7, 42. Try that. Notice the change in notation. Y equals 5 sine 4x. So pause. Okay, see what you got then. So sine goes to cos because it starts at 0 and goes upwards. It's positive straight away. 4 comes to the front. 5 times 4 is 20. 20 cos 4x. Okay, so try that one. Pause. Let's see what you would have got then. So bringing the 3 to the front. So 3 times 2 is going to be 6x squared. That is what you did in year 1. That hasn't changed. You still can have to apply the rules for polynomial functions. Cos 3x is your new one though. What do you do here? Bring the 3 to the front, and don't forget cos, which starts at 1 and goes down straight away, so it's negative, goes to minus 3 sine 3x. So well done if you got that. Okay. Try that one. F of x equals 4e to the x minus cos x. So just pause it there. Let's see what you would have got then. So 4e to the x stays as 4e to the x. That bit doesn't change. Cos x starts at 1 and comes down, so therefore it goes to minus sign, but minus, and the minus makes a plus. So very well done if you got that. Try that one. Just pause there. Okay, so the first thing you probably want to do is change 1 over e to the 3x to e to the minus 3x, and then once you know it's e to the minus 3x, you can rewrite it as minus 3e to the minus 3x, and then that e to the 3x can go back underneath. Okay, so I'd accept minus 3e to the minus 3x as a final answer as well. Try this one. So y equals 3 sine minus 2x plus 2 root x. So just pause it there. Okay, let's see what you would have got then. So first things is this, 3 sine minus 2x. So the minus 2 can come to the front to make minus 6. Sine starts at 0 and goes positive straight away, so that's going to go to cos. So we've got minus 6 cos minus 2x. Remembering that part stays the same. This part here, I would think about writing it as 2x to the half, because the square root is a half. So 2x to the half, and you can follow the rules of polynomials. Bring the half to the front, so 2 times a half is going to be 1. X to the power 1 plus to 1 minus 1 gets you minus a half. So notice that's where that bit comes from. So 2 times a half gets 1. X to the minus a half is the same as 1 over root x. Okay. Right, last one then. Have a go at this. Okay, just pause it there. Right, see what you would have got then. So 3 comes to the front to make 6e to the 3x. This 3 can come to the front here, so you've got 3 times 6. So 6, 12, 18. Sine goes to positive cos, so you've got 18 cos 3x. 5x just goes to 5, and of course any constant value like minus 4, just differentiate it to 0. So well done if you managed to get that as your final answer.